Samples are an important part of EViews and allow you to easily work with different parts of data. You will learn how to use EViews' deep understanding of time frequencies to easily select different date ranges. Economic and financial data are rarely homogeneous. A long time series often contains different regimes or periods with distinct characteristics, such as a financial crisis or a pandemic. Analyzing the full timeline can obscure these critical dynamics. The unique signal from a specific period can be lost in the overall noise of the entire dataset. The key is to isolate these specific regimes for analysis without permanently deleting or altering the underlying data. This is where EViews samples excel. Samples in EViews act as a mask. They do not delete data from the workfile, they simply exclude observations from current calculations. At its core, EViews evaluates samples using Boolean logic. Think of it as a set of conditions that an observation must meet to be included. The fundamental principle is the intersection rule. An observation is included in the active sample only if it satisfies all specified conditions simultaneously. This means it must fall within the specified date range and the logical condition must evaluate to true. If either part fails, the observation is excluded from the current analysis. The decision matrix shown visually represents this. You first define your analysis scope. Then, you decide if you need a specific period, which involves using date pairs like 1990 to 2000. Concurrently, you might decide if you need a specific economic condition, which involves using if conditions, for example, if GDP is greater than 0. The active sample is formed at the intersection where both your time criteria and your condition criteria meet. First, we have the GUI, or Graphical User Interface. This is accessed through the menu via Proc, then Set Sample. It's very visual and the best starting point for beginners. Second is the command line. This is for users who prefer speed and scripting. You simply type the command, for example, sample, followed by your criteria. It's incredibly efficient for quick, temporary checks. Finally, for complex or repetitive tasks, you can use sample objects. These are saved, reusable filters. You can define a complex set of criteria once, save it as an object, and then apply it to multiple equations or models with a simple command. When using the command line, you define a date range with a start date and an end date, separated by a space. The range is inclusive, meaning both the start and end dates are included in the sample. EViews is very flexible with date formats. For quarterly data, you can write 1990 Q1 or 1990:1, and EViews will understand both. There are also helpful keywords. At first refers to the first observation in the workfile range, at last refers to the final one, and at all resets the sample to include every observation. To set the sample to the first quarter of 1990 through the fourth quarter of 2000, you would type the command SMPL 1990 Q1 2000 Q4. It's that simple. Specifying dates is only half the story. The real power comes from combining this with logical conditions. The if clause allows you to filter data based on a logical condition. The active sample becomes the intersection of the time range and the observations where the condition is true. EViews uses Boolean evaluation. If the condition is true, the observation is included, represented by a 1. If it's false, it's excluded, represented by a 0. Crucially, missing values, or NA, not available, are treated as false. This means any observation with a missing value for the variable in your if condition will be automatically excluded from the sample. For example, the command sample at all if inflation greater than 5 will create a sample that includes all observations in the entire workfile range, but only for periods where the inflation variable was greater than 5. This slide differentiates between two types of samples in EViews, the global sample and sample objects. A global sample is a temporary filter that only affects your current view and calculations. It's like flipping a light switch. Once changed, the previous setting is gone. In contrast, a sample object is a permanent filter that you save within your workfile. You can define a complex set of criteria once, save it with a specific name, and then recall it anytime you need it.
In the workfile window, sample objects are easily identifiable by a yellow folder icon with a double arrow. To apply a saved sample object, you can simply double-click its icon or use the command SMPL followed by the object's name. This allows for efficient reuse of complex filtering conditions across multiple analyses.
The workfile window header provides crucial information. The range shows the physical limits of your dataset, the total number of observations available. This is fixed. The sample line, just below it, shows the active subset you are currently working with. This is dynamic and will change every time you set a new sample. You can change the sample in several ways: through the main menu, Proc, Set Sample, by clicking the Sample button on the toolbar, or most conveniently, by double-clicking the sample text directly in the header. In the image, the full range is 465 observations from 1888 to 2004. However, the active sample is only 13 observations from 2001 to 2004. Any calculation performed now will only use these 13 data points. Now, let's see what happens when you double-click that sample text and open the dialog box. The Set Sample dialog box, accessed through the GUI, is split into two main fields, reflecting the intersection rule we discussed. The upper field is for date range pairs. Here you enter your start and end dates, or observation numbers. The lower field is for the if condition. This is where you type your logical expressions, like unemp greater than 5. You can leave this field blank if you only want to filter by date. As shown, entering 1990-2010 in the top field and unemp greater than 5 in the bottom field will create an active sample of all observations between 1990 and 2010 for which the unemployment rate was greater than 5%. Theory is great, but let's walk through a practical case study to see this in action. For our case study, we'll use a dataset named mydata.wf1, focusing on the variable returns. The full data range spans from January 1973 to December 2006, containing 408 monthly observations. As you can see from the plot, the data is very noisy, with many positive and negative values. Our goal is to filter this data to analyze only the months with positive returns, ignoring negative or zero returns. This initial state represents the full sample, containing high noise and mixed positive and negative values. Here is the command to achieve our goal. We type SMPL, followed by the start and end dates, then the if clause with our condition. The logic here is to exclude all loss months, which are any months where the value of the returns variable is not greater than 0. After running this command, the number of observations in the active sample, which we denote as n, will decrease significantly as all the negative and zero return months are now filtered out. The command shown, sample 1973M1, 1978M12 if returns greater than 0, filters the data from 1973 to 1978 to include only months where returns were positive. The chart visually confirms this, with all points below 0 now grayed out. Now that we've applied the filter, let's look at the output of a simple analysis. After setting the sample, we can run any analysis, like calculating descriptive statistics. Notice the mean is now 0.045. This is the average of only the positive returns. The most important number to check is observations, often denoted n. It shows how many data points met our criteria. Here, it's been reduced from the original 408 to just 35. As a best practice, always verify the sample line in any EViews output table. This confirms that the analysis was run on the subset you intended, not the full dataset. A critical concept to understand is that samples in EViews are not static lists of dates or observation numbers. Instead, they are dynamic rules that are reevaluated whenever the underlying data changes. If you edit a data point that causes it to now meet or fail to meet a sample condition, it will be automatically included or excluded in the next calculation you perform. For example, changing a value from -5 to +5 could cause an observation to now satisfy a condition, leading to its inclusion in the sample during reevaluation and subsequent new calculations. Sample offsets allow you to start or end your sample relative to the first or last observation in the workfile range. The format is at first plus, followed by n, to skip the first n observations, or at last minus, followed by n, to exclude the last n observations. This is extremely useful in time series analysis. For example, when you create a lagged variable or a first difference, the first observation becomes NA, or not available. Using an offset like at first plus 1 lets you easily exclude this missing value from your analysis to avoid errors. If you calculate the first difference of GDP, dGDP, the very first observation for dGDP will be missing. To run a regression, you would set the sample using the command SMP at first plus 1 at last to start the analysis from the second observation, where you have valid data. After you've finished an analysis on a specific subset, it is critical to reset your sample back to the full range. Forgetting to do this is a very common source of errors. The command to do this is SMPL at all. This is arguably the most important command to remember when working with samples. Make it a habit to end every block of analysis with SMPL at all. You can always verify that the reset was successful by checking that the sample line in the workfile window matches the range line. First, remember that samples are non-destructive filters. They hide data from calculations, but never delete it from your workfile. Second, the two main tools for filtering are date pairs for setting specific time ranges and if conditions for applying economic or logical rules.